Good morning. In this video, we will discuss arithmetic for computers, which is floating point. Okay, let's see the floating point. Um, Going beyond the signed and unsigned integers, like signed and unsigned, like positive, negative, and unsigned integers, programming language supports certain other type of numbers, not only the integers. Programming language do support other type of numbers called fractions. They are called real numbers in mathematics. Okay, and in programming language we call them floating point numbers. Okay, so let's see some examples of real numbers, like a very simple or small number to a large number. Let's see this one, the first example. This is the pi value, which is 3.14, etc., etc. And this is another value like 2.71828, etc., etc. This one, this is actually second in nanosecond, by the way. 0.0000000001 power. So here, when you put this in 1 point something, it's 1.0 10 power minus 9. Okay. So you have an exponent here, 10 power minus 9. Another example, you can say this long number, you can convert it into 3.15576 10 power 9. Okay. So these are some examples of the real numbers, like ranging from small to big, having some exponents, 10 power something. Okay. So let's see alternative notation for the last two numbers. So ignore the first two, the last two numbers. So alternative notation for the last two numbers. This is the last two number is called scientific notation because it has a kind of number which has a mantissa and exponent like this one, 1.0 times 10 power minus 9, and the last one 3.15576 10 power 9. So this type of notation of real number, representing a real number like this in this notation, this is called scientific notation. Remember, single digit to the left side of the decimal point. You see the decimal point to the left side. Here I have 1. Okay, only one digit. Okay, so let's see this number. You have single digit to the left side, which is 3. 3 point. To the left of the decimal point, you have a single digit. Okay. So let's assume if you have a number in the scientific notation that has no leading zero, that is called normalized number. Like leading zero means in front of the binary point, the decimal, sorry, it's not binary point, decimal point. So to the left of the decimal point, if you have no zeros, that is called normalized number. Normally we try to write number in this way. So we try to write the real numbers, means the floating point number, in normalized form only. Okay, so let's see the scientific numbers. Okay, let's see in depth, in detail. Okay, let us a single non-zero digit to the left of the binary point. Now we are looking into binary floating point number. So the point is called binary floating point. Previously we saw decimal floating point. So that the point is called decimal point. Now we are looking into binary a real number. So it's called binary point. You see to the left of the binary point, you have a single non-zero digit. In binary, which is the single non-zero digit? 1. Because binary means it's either 1 or 0. A non-zero digit is 1, of course. So you have plus or minus 1 point something something something. Okay, and 2 power something. Okay, then this is the representation of binary floating point number. So here we write 1.xxx. So this is called Mantissa, or you can call it fraction. Sometimes we call Mantissa, sometimes we call fraction. And then you say 2 power y, like 2 power 2, power minus 5. So that minus 5 or 2 power 6. So that 6 is called exponent. Okay. So the y is called exponent. And after the point, what number you have, that is called mantissa. Okay, so there are three advantages for the normalized form. So writing a floating point number in normalized form has three advantages. So what are the three advantages? So the first advantage is given here. It simplifies the exchange of data that include floating point number. So you can easily write a floating point number. That is simplifies the conversion. Okay. It simplifies the floating point arithmetic algorithms. Like if you want to add something or if you want to multiply two floating point numbers. So having the normalized form, it simplifies the arithmetic calculations. Okay. And it increases the accuracy of the numbers that can be stored in a word. Okay. So mean to say you don't have unnecessary leading zeros. So you have a bit to the left to the binary point. So you don't have unnecessary zeros. So the accuracy of the numbers are maintained. Okay, so these are the three advantages of having or writing a floating point number in normalized form. Okay, it's a scientific notation but normalized form. Remember, normalized form means having one single non-zero digit to the left of the binary point or decimal point. Let's see the floating point representation in the computer. Okay. So the floating point representation must find a compromise between the size of the fraction, size of the exponent. So you need to find out what should be the number of bits, the size for the mantissa. Mantissa means fraction, number of bits for the exponent. We need to compromise on it. Can't be same. Okay. We need to compromise the size of the mantissa, size of the exponent. So let's see. The trade-off is between precision and the range. Okay. So increasing the size of the fraction enhances the precision of the fraction. Okay. Increasing the size of the fraction. So fraction, if you increase the size of the fraction, the precision of the fraction is better. It enhances the precision. Okay. By increasing the size of the exponent increases the range of numbers that can be represented. So either this way you have some positive things. Okay, if you increase the size of precision, it does something. If you increases the size of the mantissa, it does something. Okay. So let's see. Floating point numbers are usually multiple of the size of the word. Word means it is going to be 32-bit. Remember, a word means it's 32-bit. Okay. So let's say how these 32 bits are going to be distributed for the fraction, for the exponent, and for the sign bit. Let's see all those things. Okay. Here, this is the representation. Oh, sorry. This is the representation for the floating point number for the MIPS architecture. So I told you word means 32-bit. 32-bit means how the bit position starts from 0 to 31. Can you see? The position starts from 0 to 31. The 0th bit is called least significant bit. 31st bit is called most significant bit. Okay. Let's see. So you have some arrangements. The most significant bit, this is the bit number 31, is for the sign. So S is the sign of the floating point number. What do you mean by sign? If the bit is 1, the number is a negative number. If this sign bit is 0, the number is a positive number. That's one thing. Next thing is, the next 8 bits are given for the exponent. You know, exponent means 2 power minus 6. You write something, 2 power 2, 2 power 5. So that 5 is called exponent. Okay, so 8 bits are allocated for the exponent. So 1 for the sign bit, 8 for the exponent. So the remaining 23, because the total is 32 bit. So this 23 bit is for the mantissa. So what is a mantissa? You know, you write a number like 1.001. That 001 after the decimal binary point. The right side of the binary point, you have some digits. That is the mantissa. 23 bits are assigned for Mantissa. Another name for Mantissa is fraction. Okay, so in general, if you want to write a floating point number, you can represent like this. This is the idea, like minus 1 power s, okay, into fraction times 2 power e. E means exponent, f means fraction, s means the sign bit. Okay, if the sign bit is 1, minus 1 power 1. What is minus 1 power 1? Minus 1. That's a negative number. Let's say the sign bit is 0. So minus 1 power 0. When you say minus 1 power 0, it's going to be anything power 0 is 1. Positive 1. Alright. Okay, so this is the idea of the fraction. The representation of the floating point numbers. Okay. These chosen sizes of the exponent and the fraction gives MIPS computer arithmetic an extraordinary range. So that means that the fraction almost as small as 2 power 0, 10 power minus 8 and up to, this is a negative number, up to 2 power 2.0, 10 power plus 38. So 10 power minus 38 to 10 power plus 38. This is the range of numbers that you can express. Yeah, this is for the decimal. 10 power. It's a decimal floating point number. The overflow interrupts can occur in floating point arithmetic as well as in the integer arithmetic. The overflow we already discussed in the multiplication or in I think in other topic. Overflow means the exponent is too large to be represented in the exponent field. In the previous slide I told you how many bits are allotted for the exponent, 8 bits. For example, if you have a floating point number, that number, it has an exponent that cannot be represented in 8 bits. It needs more bits. That's the meaning of overflow. Okay, so you need to know the meaning of overflow. Overflow means what? Okay then. So the floating point offers a new kind of exceptional event as well. Like if non-zero fraction is too small to represent, underflow interrupt occurs. So not only overflow, underflow also we have. For example, if a non-zero fraction is too small to represent. So you have a small number and it's very small to represent, then that is your underflow. Okay. So let's see the double precision. The whatever we see before, the 1 bit for the sign and 8 bit for the exponent and 23 bit for the fraction, that is for the single precision number. Now double precision. Double precision means double the size. So instead of having 32 bits, here you will have 64 bits. Okay, then now we will have 64 bits. So what is this? One way to reduce the changes of overflow and underflow is to offer another format. What is the another format? Double precision range. So that you can avoid the overflow problem or also the underflow problem. Okay then. So here in the double precision, so here is the representation. Of course, 1 bit is for the sign. Okay then. And the 8 bits, normally we give 8 bits for the exponent, is it? So now 11 bits for the exponent and then 32 plus 2, because here you have 64 bits. Can you see here 64? 64 means 2 word. The one on the top is the first word, the one below is the second word. The second word is having 32 bytes. The first word is broken into sign bit, 11 bit for the exponent and 20 bit for the fraction. Continue the fraction, 32 bit in the next word. So 32 plus 20, 52 bit for the fraction. Okay. So this is the double precision floating point representation. So MIPS double precision allows, so what is the range of numbers allowed in the double precision is 2 into 10 power minus 308 to plus 308. This is the range of the numbers that you can represent in double precision. Okay, so this is the idea. Primary advantage is its greater precision because of the much larger fraction. Okay. So here other formats. So these formats go beyond the MIPS. So they are part of the IEEE 754 floating point standard, which was invented in 1980. This standard has greatly improved both the ease of porting the floating point programs and quality of the computer, arithmetic, etc., etc. So IEEE 754, it makes the programmer to have the programs easy to write floating point programs and to do quality arithmetic operations. So the IEEE 754 floating point. So it's 32 bit long. So it is going to be divided into some fields, fixed size fields. So what are the fields? Same like before. The most significant bit. The bit number 31 is for the sign bit. Okay. And then 23 bits are for the Mantissa, and then 8 bits are for the exponent. It's same like the previous one what we see before. And here the Mantissa represents so let's say the Mantissa represents a number in 24-bit base. Two possible notation, that's like, let's say if you have a number 1.xxxx etc etc, that are the, let's assume that you have 23x. This is very tricky because Mantissa means, I told you in the last slide, Mantissa is given 23 bits and exponent is given 8 bit and there is one sign bit. So we have a 23 bit for the fraction, that is the Mantissa, but 24 bit number that starts with a 1. So the 20th place, the ones place is assumed to contain a 1, okay, and is not present in the Mantissa. So this trick gives us 24-bit precision only with the 32-bit. So if you have a bit like 1 point, for example, let's assume that you have a bit like this 1.1111 and then 000010 11 011 010 1001. So this is your number. Okay. Let's assume how many bits you have. 1, 2, 3. Here got 4, 5, 6, 7, 8, 9, 10. So here you have 23 bits. Okay. And with this 1 bit, because you have a bit to the next to the binary point, to the left of the binary point. So including that bit, it's now 24 bit. So the binary number of this floating point number is 11111 etc. Remember. Okay. But that 24th bit is not presented in the Mantissa. But when you consider Mantissa is just these bits which is to the right of your binary point. We don't consider this one. Okay, don't consider this one. Okay then. So remember this one. So let's say how the Mantissa works. Since I told you leading zeros of a binary number is going to be dropped, so you are going to include the first one, because if your number is 1 point something, you are going to not represent the 1. You are not going to represent. You are going to concentrate on the digits after the which comes after the binary point. Okay. So there will always be 1 to the left of a binary point, because I told you normalized form. This is your normalized form. You are writing a normalized form. What I said, you need to have a single non-zero digit to the left of the binary point. So this one you are not going to represent. You are not going to write it. Okay, you are not going to represent this number. Okay. So let's assume that you have a number like this. What is your number? Okay, here we'll start from here. Let's assume that you have a number like this: 00011.0010 1101. So you have a floating point number like this. What are you going to do is, we are not going to bother about the leading zeros. You have leading 0, 0, 0, 0. So that leading 0 will be removed. So drop the leading zeros. So what is the left? 11.00101101 because you ignore the leading zeros. Now what the normalized form says, single non-zero digit the left of the binary point, but the left of the binary point I have two non-zero digit. I want only one non-zero digit. Okay, so only one should be there, is it? So let me keep it. So move the binary point to the left. So you will have 1.100101101. As you move the binary point to the left, you will have 2 power 1. Okay, so you have the exponent 2 power 1. Do you get the idea? So this is the idea of the how to represent a number, a floating point number in normalized form. Okay, but in reality, what is the number I'm going to represent in the computer is the Mantissa. This is the Mantissa. After the binary point, what do you have? 100101101. This is what you call Mantissa, and this is what you call exponent. Okay, a sign bit. It is a positive number, so sign bit is 0. Fine. This is the idea. Okay then. Okay, let's move on to the some more explanation on exponent part. We say the exponent. Okay, there's 8 bits for the exponent, which is starting from bit number 23 to 30. This bit number, I'm talking about bit number, not the bits number. No, it's not the number of bits, bit number. So bit number 23 to 30 is for the exponent. That means 8 bits are assigned for the exponent. So the exponent is an integer. Sometimes it may be a negative number, or it may be a 0, or it may be a positive number. What is the exponent? You know, normally you write 2 power 2, 2 power minus 5. So if I say 2 power 2, power, what do you write in the power? 2. It's a positive. Sometimes we write 2 power 0. So exponent is a 0. Sometimes we write 2 power minus 6. So minus 6 is a negative. That is the exponent. Okay. You may guess that an 8-bit 2's complement integer would perfectly work for this, but different type of notation we are going to use for the exponent. Okay, because it may have a negative number, positive number, sometimes it may have a 0. So the exponent is expressed using a biased integer. The true exponent is added to plus 127. Remember, what is your exponent? Let's say 2 power minus 5. So the exponent minus 5 is added to 127. Minus 5 plus 127. What do you get? 122. So that is the unsigned binary integer. Okay then. So the biased integer is encoded in the 8-bit number. So 125 or 2 you get, is it? Because I say 2 power minus 2, sorry, minus 5. That minus 5 is added with 127. You add it, you get positive 120. 122 is the unsigned number. You are going to write the 122 inside the 8-bit position. Okay. If you write number 127, the actual exponent is 0. If you get 128, the actual exponent is 1. If you get 126, the actual exponent is minus 1. 0 plus 127. 1 plus 127. Minus 1 plus 127. You try to add the real exponent. Try to see what is the unsigned binary integer, biased exponent. This is what you call biased exponent. This is the biased exponent. I am going to write it in that 8 bits. Okay, so you need to calculate this exponent. Okay, let's see examples. Let's some more explanation for exponent. So exponent bias for double precision is 1023. Okay, the biased exponent ensures that the exponent is unsigned. In order to get back the real exponent, biased exponent is subtracted from the unsigned representation. So when you add your original exponent with the 127, you get the biased exponent. If you want know, you have the biased exponent, you want to know the original exponent, so subtract 127. That's it. Okay. So this is the idea. There got some exceptions. Let's assume there is a floating point number which is 0.0. What do you mean by 0.0? There is no mantissa. So the mantissa is going to be 23 zeros because there is 23 bits for the mantissa. So all the bits will be 0, 0, 0. Exponent. Do you have an exponent here? The number is 0.0. So there is no exponent. So when there is no exponent, what do you say? What I say just now? You need to add the original exponent to 127 to get the biased exponent. So 0 plus 127. So what do you get? 127. You get the biased exponent 127. How come you have, it is illegal to have an exponent of 0 for a non-zero mantissa. Okay, so this is one thing. This is an exponent, exceptions for the exponent. Let's assume there is one other example. The exponent 255 for a decimal number. This one. This is a decimal number. Let's assume the exponent is 255. In binary it is 11111111. 8 ones. Okay. It's used to signal various problems such as you will get a division by 0. So these are the two exceptions for the exponent. Let's see one example on how to convert a decimal to a binary fraction. Okay, you are given a decimal number, you are going to convert to a binary. Okay, you are given a decimal floating point number, you are going to convert to a binary floating point number. This is the idea.
Now let's discuss how to convert decimal to a binary fraction. Let's assume you have a decimal number. You are planning to convert the decimal number to a binary number. Okay. So this is the decimal number 0.8125 base 10. So this is a decimal number. So how are you going to convert? You take the number which is the fraction part 0.8125. You multiply by 2, you get some number like you have 1 point something, is it? So the 1 you keep it, okay then, and then 0.625. So that 0.625 into 2 you get 1.25. So you keep the 1, okay, then you got a 1 from here and another one from here, and then you got 1.25, is it? So take the 0.25 into 2, you get 0.50. So left to the decimal point you get 0, right to the decimal point you get 5. Okay, so take the 0.5 into 2, you get 1.0. So you get a carry 1. Okay, so this is the decimal representation of, okay, so you put a point in the front. So this is the binary representation of this decimal fraction number. The same goes with the another number. Let's assume you have 0.6875. So multiply that by 2, you get 1.375. So you get 1. Okay, before the decimal point. To the left of the decimal point you get 1. Right of the decimal point you have 375. So that 0.375 into 2 you get 0.75. So 0. The carry is 0. 0.75. Multiply it with 2 you get 1.5. So what is the carry? 1. Okay. 0.5 multiply by 2 you get 1.0. So the carry is 1. So 0.1011. This is the binary fraction of the decimal fraction. So let's see one other example. Yeah, let's see one other example. This is reverse. Like you have a binary and then you are going to convert to a decimal fraction. So you are given a binary fraction, you are going to convert to a decimal fraction. So let's see. This is your binary fraction 0.1011. So how are we going to convert is very simple. So you have from 0.1011, is it? So with this number you multiply 2 power minus 1. With this number you multiply 2 power minus 2. With this number, this is 2. With this digit you multiply 2 power minus 3. And with this number you multiply 2 power minus 4. Can you see here? With 1 you multiply 2 power minus 1. With 0, 2 power minus 2. With 1, 2 power minus 3. With the last one you have 2 power minus 4. So you get some answer like 0.0625, 0.125, this is 0, this is something 0.5. When you add all those things, let's do the summation, add, you get 0.6878 base 10. So this is the answer. This is the answer. Okay. Let's assume you have a 0.10. This is your number 0.10. So you multiply like this. In case if you have something before the binary point, also after the binary point. So after the binary point you multiply 2 power minus 1, 2 power minus 2, 2 power minus 3. Before the binary point you multiply 2 power positive exponent. Like this one you multiply with 2 power 0. This 0 you multiply with 2 power 1. This one multiply with 2 power 2. And then this last one multiply with 2 power 3. This is what it's written. 2 power 3, 2 power 2, 2 power 1, 2 power 0. And then the rest after the decimal point. I just show you how to do. So you add up all those things, you get this answer 13.4375 to the base 10. So next we move on to the floating point examples. So now let's have some other examples. Ieee representation. Okay, let's assume that minus 0.75. You have a number called this one 0.75 to the base 10. So you're going to represent in a single precision and also in the double precision. So let's do the single precision and double precision. So 0.75 when you multiply by 2 you get 1.5. So the carry is 1. 0.5 you multiply by 2 you get 1. Okay. So 0.11 to the base 2. This is the decimal representation. Just now I show you how to do. So this is the decimal representation. But I told you this is, when you want to write it in a scientific notation, I need an exponent. So you can write 2 power 0. When you say 2 power 0, anything power 0 is 1. So the value is still the same. Okay. But it is not a normalized form. What is a normalized form? To the left of the binary point, you should have a single non-zero digit. But here, this is the binary point. To the left of the binary point, I have a 0 digit. The digit which is a 0. I said single non-zero digit. I should have a 1. So you need to move the binary point here. So 1.1 to the, when you move the binary point to your right, you minus 1 to the exponent. So it was 0. 0 minus 1, it's minus 1. Okay, when you move the binary point to the right, you add a minus 1. to the exponent. Whatever exponent you have currently, minus 1. If you move the binary point to your left side, plus 1 to the exponent. Okay. So this is the idea. Actually, the general representation of your single precision is, this is the one I explained in the previous slides. I mean, quite few slides back. For sign bit, you are going to have this minus 1 power sign bit and 1 plus whatever fraction you have. Okay. And then 2 power whatever exponent plus 127. So let's see this number. Your number is 1.1. 2 power minus 1. So this is your number. I'm going to represent in single precision, which is 32 bit. 32 bit means 1 bit for sign, 8 bit for fraction, and 23 bits for the exponent. So this is what our alignment. Okay then, so here it is. The sign, what is the sign of this number? It's a positive number, 1.1, 2 power minus 1. This is a positive number. So, minus 1, power 1, sign bit is 1. It's a negative number. On the top it's written here, so sorry, here it is. It comes from negative 0.75. So, it's a negative number. Actually, it's a negative number, minus 1.1, 2 power minus 1. So, minus 1 and the sign bit is 1. So, this is 1. Multiplication. 1 plus the fraction. So, what fraction this is your fraction. Fraction means Mantissa. Okay, so 1 plus the fraction. Remember, fraction takes 23 bits. Exponent take 8 bits. Okay. So, 1 plus the fraction, 0.1. When you count the bits, you will have, see, 4 plus 4, 8, and then 12, and then 16. And then this is 20 and then plus 3, 23. Can you see here, when you count the number of bits, the fraction will be taking how many? 23 bits. Okay. And here for exponent, the formula says 2 power the original exponent plus 127. Original exponent is minus 1 plus 127. Okay. So let's see the same example, the same decimal number, which is minus 0.75. So this is your number, minus 0.75, and you are going to put it in the single precision, also in double precision. Okay, single precision, I told you, we just calculated. The sign bit is going to be 1, and then the fraction, which is this is exponent, 8 bit for the exponent. What is the exponent? In the previous slide I told you, original exponent plus 127, which is minus 1 plus 127, it is 126. So this is the binary representation of 126, the 8 bits. When you compute, you know already how to calculate the decimal of binary to decimal conversion. So this bits, which is 0, 1, 1, 1, 1, 1, 1, 0. This 8 bit is 126. And the remaining 23 bits is for the Mantissa fraction. Okay. And this is the same representation for the double precision. So this is the formula for the double precision. Okay then. Okay, let's see the binary to decimal one more. So you have this binary bits 1 1. This is the binary bits. You have given a 32 bit. You have given a 32 bit, which is 1 1 0 0 0 0 0 0 1. Etc, 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 etc. This is the 32 bit of the binary. This is a single precision floating point number. I want to know the corresponding decimal floating point number. Okay, I want to convert this binary 101010 into a decimal number. Okay, so you are going to apply the formula to get the decimal number. Okay, do you remember previously what we do for sign bit? Minus 1 power sign bit. Okay, and then 1 plus the fraction. This is the same for the previous conversion on this conversion, and this is different. What is your original exponent? Plus 127. That was the previous case. Now what are you going to do is exponent minus biased exponent. Okay, so this is the idea. So the exponent field here, you have here from this bit to this bit. This is your exponent field. What is the number you have? 0 1 0 0 0 0 0 0. What is this exponent? It is in decimal. It is 129. Okay, this is 129. Can you get the idea? This number 129 minus 127. Now you subtract 127. Before we add 127. Now you subtract 127. So 129 minus 127, you get 2. See, you get a 2. 2 power 2. What is 2 power 2? 4. So multiply minus 1.125. Sorry, minus 1.25 into 4, you get minus 5.0. So this is the decimal equivalent of this long binary single precision number. This is the formula. You have to remember the formula. Here only one difference is here. Before, what do we do? Whatever the exponent, we add 127 for the previous example. What is the previous? Decimal to binary. When it is binary to decimal, whatever the exponent, minus 127. Okay, minus 127. Okay. Now let's do the addition in floating point. So we can do the arithmetic operation on the floating point numbers. So let's assume that you have two numbers. Let's deal now decimal, not the binary, to the base 10. Okay. So you have this number 9.999 to the base 10, 10 power 1. Another number is 1.610, 10 power minus 1. So you have two numbers. Okay. Now you need to see the exponent part. Okay. We can't add straight away because the exponent is 10 power 1 here. This is 10 power minus 1. It has to be same. See, for floating point addition, the exponents have to be similar. We can't add a different exponents like this. You have to do some adjustments. So what is the thing you need to do? So first step is, let's see the smaller number and then make it as a big number. Okay, when you see 10 power minus 1, this is small. 10 power 1 is big. Am I right? Okay, just have this way. So this is small. This exponent 10 power minus 1 looks so small. Minus 1, negative 1. So you take that number 1.60610, 10 power minus 1. You make the exponent very similar to this exponent. It is 10 power minus 1. Make it as 10 power 1. Okay. How do you make it 10 power 1? When you add minus 1 plus 2, you get a 1. Is it? To this exponent, if I add plus 2, you get what? You get a positive 1. So what you need to do? Move the decimal point to your left side. 1 time, 2 time. Okay, so this is 1 time, this is 2 time. When you move it 2 time, you add 2. How many position you move to the left? 2 position. So you add 2. So minus 1 plus 2. You get 10 power 1. Now you got this number 0.016. You round it because it's all rounded. So I just keep 0.016. Okay. Now we can try to add the next number. What is the second number? I mean the first number is 9.999 With this, just now we found this number. When you add, you get 10.015. Okay, so this is the answer, and 10 power 1. This is the exponent part. But you see, this is the decimal point. Before that, mean to the left of the decimal point, I need to have single non-zero digit. But I have two digits, 10. 10 is two digits, is it? No, I should have single non-zero digit. So let's move this point one position to the left side. Okay. So when you move one position to the left side, what you do? You add to the exponent, you add a 1. So it will become 1.0015 10 power 2. So now this is in normalized form. Normalized form means to the decimal point, to the left of the decimal point, you have single non-zero digit. So let's see. So now this is last step. You already have the answer, which is 1.0015 10 power 2. If you would like to round the number to keep 3 decimal, including the single non-zero digit, so you want to keep 4 decimal numbers, okay, like this. So you can round it 0.0015. So 5, it's above 5 or above 5, you can turn it to 2. So 1.002. So you can round to keep 4 digits. Okay, so this is possible. Now let's move on to the multiplication. Yeah. So this is the multiplication algorithm. So here, this is the normal path to execute step 3 and 4. Okay. So what you do for the multiplication? Very simple. First step, you are going to compare the exponents. You know, like for example, I have 1.75 into like for example 10 power 2, and another number is 2.01, for example 10 power minus 2, something like that. So here you are comparing the exponents of the two numbers, and then you are going to shift to the small number to the right until the exponent matches with the, this is the addition, floating point addition. Okay, floating point addition algorithm. So you are going to see the small number 10 power minus 2, you are going to make it as like a big number. So by how do you make it big number? So you are going to shift the smaller number to the right until its exponent matches with the large exponent. Do you get my point? When you add a plus 4, you will get 10 power 2, is it? So that means you will be moving this 4 places to the left. Okay, and 1 place, 2 place, 3 place, and 1 more. Something like that. Okay. And then after that you add the fraction, and later on you keep the same exponent. That is the, whatever we see in steps, this is the same thing explained in this algorithm. Whatever I explained in the previous slides with example, the same steps is explained. So this is some more example. So now let's do the binary multiplication. Oh, sorry, binary addition. I'm sorry, I'm telling by multiplication. We are talking about addition. So let's try to add the number. So the question is 0.5. This is to the base 10. And you have negative 0.4375. So I'm going to add in binary. So first I have to convert this number to binary. You now know how to convert. So to this number 0.5 multiplied by 0, you get a carry 1, and then 1.0 you get 0, is it? With that 0 you multiply, you get carry 0. So with 0.0 you multiply 2, you get again carry 0. With 0.0 you multiply 2, again you get carry 0. This is 0.1000. Okay, so this is not in the normalized form. Let's keep it in normalized form. So move the decimal binary point to your left side, to your right side. So it will be 2 power, this is binary number, 2 power minus 1. Because I told you, when you move your binary point or decimal point to your right side, add minus 1 to the exponent. You don't have exponent. What does it mean you don't have exponent? It's 2 power 0. Then minus 1, it becomes 0 minus 1 is 2 power minus 1. Something like that. And the same goes with the next number. You have another number. When you multiply, you get 0.0111. Again, this is not in a normalized form. Move this binary point to two digits to the right. So it will become 1.11, 2 power, 2 places you move to your right. So minus 2. So it's here. Okay then. So actually they want to, let's keep same number of digits. Here we have 4 digits. So here we have 3 digits. So add a 0. It's not a big deal. There is no meaning for the zeros, this zeros. Okay. So you can add a 0 at the end. It doesn't have meaning. Then now you have the binary representation. Now you can add the number. As like the previous steps, we discussed how to add the number. So as like the previous step, you can add and you can get the result. So what are the two numbers now? You have something with 2 power minus 2, another one with 2 power minus 1. Which is the smaller? Remember, minus 2 is the smaller. Don't think minus 1 is smaller. No. In negative, the number looks bigger is the smaller. Okay, so minus 2 is the smaller. So make it as minus 1. Make it similar to this one, minus 1. How to do? When you add a plus 1, it becomes minus 1, is it? So move the bit to the left. So it will become 0.111, 2 power minus 1. Okay. Is it clear with you all? So this is the number. And now you have the other number, which is just a second. Okay, from the calculation you may have another number. It's in the previous slide. So when you add those number, when you try to do the other number, you will normal addition. So now you add the fraction part and then you keep the same exponent, which is 2 power minus 1, and later on the result, normalize the result, and if you want you can round the result. So this is the idea, you can do it. Okay, thank you.